For the following sequence of reactions, the correct products are. Now benzene, first it is treated with bromine in the presence of iron and then it is heated. So it will cause bromination of benzene and this is the bromobenzene formed as product. Now next, treating with magnesium and dry ether, we get the Grignard reagent C6H5MgBr. On treating with alcohol, methyl alcohol, MgBr will leave as MgOCH3Br. Here CH3OH will break as CH3O minus and H plus. So MgBr will leave as MgOCH3Br and H plus ion will attack the benzene ring, forming pure benzene. So the correct option is option 1. So this is the product formed and this is the another product formed. Arrange the following conformational isomers of N-butane in order of their increasing potential energy. The correct option is option 2. If we consider the structures, this structure 2 is eclipsed and structure 1 is a staggered conformation. In this structure 2, this is eclipsed isomer and the methyl groups which are big in size are very near to each other. So potential energy of the structure 2 is highest. In structure 1, it is the staggered conformation and the methyl groups which are bulky group are opposite to each other, as far away from each other as possible. So the potential energy of 1 is minimum. So 1 has minimum potential energy and structure 2 has the maximum potential energy. Now out of structure 3 and structure 4, structure 4 is eclipsed and structure 3 is staggered. So structure 4 is eclipsed, but here hydrogen atoms which are very small in size are near to each other. So its potential energy is less than structure 2 which is also eclipsed. So structure 4 has less potential energy than structure 2. And structure 3, it is a staggered conformation, but even though it is a staggered conformation, the bulky group methyl groups are not as far away from each other as possible. They are slightly nearer to each other in comparison to structure 1. So its potential energy is greater than structure 1 but less than structure 4. So this is the correct order of increasing potential energy. So option 2 is the correct option. The major product of the following reaction is. Now in this reaction, alcoholic NaOH will result in elimination. So chlorine will leave as chloride ion and hydrogen present here will leave as H plus ion and these sigma electrons will form pi bond in the ring. So the resulting structure will be structure 1. So major product is option 1. Question 46. In this, alkyl halide breaks into cation and anion and then nucleophile attack forming the product. So this is SN1 reaction. SN1 reaction depends upon the stability of the carbocation. Now which statement is or are correct for this reaction? Polarity of the solvent decreases, then rate of reaction increases. No, this statement is wrong. Strong nucleophile is more suitable for this reaction. No. Now if R is bulky, then carbocation become more stable. Correct. Racemization take place in this reaction. Correct. Yes, in SN1 reaction, the product formed are optical isomers of each other. So racemization takes place in this reaction. And depending on the stability of the carbocation, that is, more is the stability of the carbocation, greater is the reactivity. So option 3 and 4 are correct. Statement 3 and 4 are correct. Correct option is option 4. The major product of the following reaction is. Now in the presence of alcoholic KOH, elimination will take place. Bromine will leave as bromide ion. Then this hydrogen will leave as H plus ion forming HBr and these sigma electrons will move to form the pi bond. So this is the product formed. CH3, CH2, C, here bromine, double bond, CH2. Then again in the presence of NaNH2 and liquid ammonia, bromine leaves as bromide ion, this hydrogen leaves as H plus ion and the final product which is formed is CH3, CH2, C triple bond, CH. So correct option is option 4. The increasing order of the reactivity of the following halides for the SN1 reaction is. Now option 1, this halide, when this carbon-chlorine bond breaks, it will give rise to carbocation, and this carbocation is secondary carbocation. Why? Because the carbon which is having positive charge is bonded to two other carbons. This halide, when carbon and chlorine bond breaks, then the carbocation formed is primary carbocation. क्यों है ये primary carbocation? Because the carbon having the positive charge is bonded to one other carbon. In case of this halide, there is a benzene ring and CH2Cl and COCH3. Now when this carbon-chlorine bond breaks, a benzylic carbocation is formed, and this carbocation is stabilized by the delocalization of the positive charge on the benzene ring. So the most stable carbocation is the third carbocation, and then out of secondary and primary, the secondary carbocation is more stable than the primary. Now since SN1 reaction takes place through the carbocation intermediate, so greater is the stability of the carbocation, greater is the reactivity of the halide for the SN1 reaction. Therefore, the order of reactivity is, this compound 3 is more reactive towards SN1 than compound 1, and compound 1 is more reactive towards SN1 than compound 2. So correct option is option 2. In SN2 reaction, the correct order of reactivity for the following compounds. Now CH3 whole thrice CCl. The carbocation formed in SN2 reaction, there is a transition state formed where the nucleophile attacks the carbon which is bonded to the halogen atom, and the halogen leaves as halide ion. Now greater is the steric hindrance around this carbon which is bonded to the halogen atom, lesser is the reactivity towards SN2 reaction. Now in CH3 whole thrice CCl, there are 3 methyl groups around this carbon, so the steric hindrance is very high in this compound. The next is CH3 whole twice CHCl. Now in this there are only 2 methyl groups around the carbon which is bonded to the halogen atom, so steric hindrance in case of this compound is less. Then there are 2 other compounds, one is ethyl chloride and one is methyl chloride. The steric hindrance is least in case of methyl chloride, and ethyl group is bigger than methyl group, so it exerts greater steric hindrance. So the correct order is option 2. Methyl chloride is most reactive towards SN2 than ethyl. Ethyl is more reactive than this compound, and the least reactive is CH3 whole thrice CCl, because the steric hindrance is highest in case of this compound, and SN2 mechanism is inversely proportional to steric hindrance. Greater is the steric hindrance, lesser is the reactivity of the alkyl halide towards SN2 reaction. Consider the following bromides. Again, correct order of SN1 reactivity has to be seen. So if this carbon-bromine bond breaks, then there is positive charge on this carbon. Now this positively charged carbon is bonded to 2 other carbons, so it is a secondary carbocation. Again carbon-bromine bond breaks, positive charge on carbon. This is bonded to 2 other carbons, this is also secondary carbocation, but in this case the positive charge is delocalized due to the presence of pi bond in conjugation with the positive charge center. So this pi bond will move here and the positive charge is delocalized on this carbon. In case of the compound B, allylic carbocation is formed, and due to the delocalization of the positive charge, this compound B is more reactive towards SN1 reaction. Now here when carbon-bromine bond breaks, primary carbocation is formed. So primary is less reactive than the secondary. So the least reactive is A, and out of B and C, compound B is more reactive than compound C, and out of A and C, C is more reactive than A because C is the secondary carbocation, this is the primary. B is more reactive than C because allylic carbocation is formed and it is stabilized due to the delocalization of the positive charge on the benzene ring. So the correct order of reactivity is B more reactive than C, C more reactive than A. So option 1 is the correct option. The major product obtained in the following reaction is, now this is a strong base, so there will be elimination reaction. Bromine will leave as bromide ion and hydrogen will leave as H plus ion, and the compound formed is alkene. So option 2 is the correct option. Question: the major organic compound formed by the reaction of 1,1,1-trichloroethane with silver powder is, ethane means 2 carbon, and carbon number 1, there are 3 chlorine atoms, so 1,1,1-trichloroethane. Now 2 moles of trichloroethane reacts with 2 moles of 1,1,1-trichloroethane reacts with 6 moles of silver to form the product. This is the product formed. This product is 2-butene plus AgCl. 6 moles of AgCl are formed. Now actually what happens, this is the reactant, this is the trichloroethane. Now considering the reaction with silver, when it reacts with silver, 6 moles of silver, there are 6 moles of chlorine atom. So on reacting with 6 moles of silver, these chlorine atoms are removed as silver chloride, and CH3C and CH3C part, it joins by triple bond, and the product formed is 2-butene. So the correct option is option 3. Next question: total number of aromatic compounds among the following compounds is. Now the rule for aromaticity is delocalized pi electron system, then the compound is planar, then it follows Huckel's rule, that is 4n plus 2 pi electrons, where n denotes the number of rings. Now suppose this is compound number 1, this is 2, this is 3, 4, 5 and 6. Compound number 1, it has 2 rings, so it must be having 10 pi electrons, but it is having less than 10 pi electrons. So 4n plus 2 pi electron rule is not followed here, so this is not aromatic. Similarly, this is also not aromatic because it does not have 4n plus 2 pi electrons. This is also not aromatic. This also does not follow 4n plus 2 pi electron rule. Now among 5 and 6, compound 5 is aromatic because it has delocalized pi electron system, it is planar and follows 4n plus 2 pi electron rule. Compound 6 does not have delocalized pi electron system, so this is also not aromatic. So how many aromatic compounds are there among the following? Only 1. Next question: the major product formed when 1,1,1-trichloropropane is treated with aqueous potassium hydroxide is. First of all, what is the structure of 1,1,1-trichloropropane? Let's write the structure of propane first. CH3, CH2, CH3. This is propane. Now, this is the first carbon, second carbon, third carbon. If all the hydrogen atoms of the first carbon are replaced by chlorine, then this becomes 1,1,1-trichloropropane. And when this is treated with aqueous KOH, this is aqueous KOH, then all the chlorine atoms are substituted by OH group. So all the 3 chlorine atoms get substituted by OH group and chlorine is removed as potassium chloride. Now 3 OH groups on the same carbon is quite unstable, so there is removal of water and Water gets removed and the final product formed is CH3, CH2, COOH. On heating, a molecule of water gets removed and final product formed is propanoic acid. This is 3-carbon acid, so propanoic acid. So correct option is option 4. Here it will be 3 moles of KCl.